Today we're going to take a little bit of a step beyond what our Think Well material talks about and dealing with the second derivative with parametric equations. We've seen the first derivative and how to calculate that using the parametric equations, and of course first derivative talks about where function is increasing or decreasing, where the graph, well, not even a function here, it might, parametric equations doesn't guarantee function, but where the derivative equals 0 would be where we have a horizontal tangent line, and so on, like we talked about in Calc 1. The second derivative, just like Calc 1, talks about where the curve would be concave up or concave down. So we'll derive the formula for the second derivative, and then you'll be able to show where the curves, the parametric curves, are concave up and concave down. So first of all, let's take a look at the first derivative, and then from there move on into how we find the second derivative. So we let x equal f of t and y equal g of t. And our first derivative then, dy by dx, is dy by dt divided by dx by dt. Or in the prime notation, we can say g primed of t over f primed of t. And of course, we always have to throw in here, provided f primed of t does not equal 0, since we have a fraction there. Now, what we're going to do is kind of rewrite some of the notation so we can find what the second derivative is. Let's look at this dy by dx. Well, ultimately, as we go through this formula, we'll end up with a function of t. So dy by dx is going to be some function of t. And then we're going to take the derivative of that to get our second derivative. Okay? Oops. So, now that we have everything put together correctly here, we're going to define dy by dx as this function of t. We'll call it r of t. And from there, when we take the second derivative then, we're going to be taking the derivative of dy by dx, which ultimately, in the practical terms, we're going to be taking the derivative of r of t, but with respect to x. And we'll see how that works out. Well, we're taking the derivative with respect to x, but our function is in terms of t. So we kind of have to convert that into terms of what x is, or t is what in terms of x. So we're saying ultimately t is going to be what in terms of x. Well, back in the definition, what we started with parametric equations, we said x was the function of f of t. So by our algebra concept of inverse functions, t is actually going to be the inverse function of x. Okay. So again, to get this all in terms of x, we'll be taking the derivative with respect to x of r of t, which we said would be the inverse function of f of x. Okay, with me so far? Now, ultimately here we are taking the derivative of a composition of functions. So to take the derivative of this, we need to do the chain rule. Okay. So we take the derivative of the outside or, well, yeah, we could, maybe let's write it a little bit different. The derivative of the outside, we'll do the prime notation. R will be the outside. Now, this isn't just r primed of x, but it's r primed evaluated at the inside function. So that would be the chain rule, the derivative of the outside part, times the derivative of the inside. Now we are doing this with respect to x. Okay, so this would be the derivative of r of t with respect to x. T, again, changing that to f inverse of x. And my notation's not real good. That's the inverse function. F inverse of x is the inside of the r primed. Okay. Well, what did we say f inverse of x was? That's our t value. So this part is going to be simply r primed of t. Okay? And then we'll have to figure out what this is. Now, before we move on to the top of the next page, remember what we're doing. This, we're looking at the second derivative of y with respect to x. So we'll kind of put this as the result so far. So up to this point, we've got the r primed of t, and then we've got to figure out how to represent this in terms of t as well. Now, we said that t was equal to the f inverse of x, so plugging that into this part, we would have dt by dx. But we really don't know what that is in this form. Let's see how we would derive dt by dx. We know, again, x and t relate this way, or it's going to be easier to look at it as f of t equals x, which is what we did earlier. That's the definition of our parametric equations, the x part. So if we were to take the derivative of that with respect to x, well, that is going to be 1, we'll pick the easy side first, dx by dx, or the derivative of x with respect to x, is 1. But here, well, we're not in terms of x, we're in terms of t, so once again we have a chain rule to work through. We would have the derivative of the outside with respect to x times the derivative of the inside, derivative of t with respect to x. Now, what is this right here? Well, the derivative of f of t with respect to x is simply f primed of t. That's what we were looking at even in the definition of the first derivative. So the derivative, maybe it's easier to see it looking at it this way, that is simply going to be f primed of t. So f primed of t times dt by dx equals 1. dt by dx, solving for that, divide both sides by the f primed of t. dt by dx is going to be 1 over f primed of t. And so, plug that back up here. Our second derivative of y with respect to x in terms of our parametric equations will be r primed of t times 1 over f primed of t. Well, what was r primed of t? We defined that. We defined r of t as the first derivative. So r primed of t is going to be the derivative of our first derivative in terms of t. Oops. dy by dx will be found in terms of t, so the derivative of dy by dx in terms of t will be this r primed of t. But our second derivative of y with respect to x, d2y over dx squared, is going to be this divided by f primed of t. And we'll look at a couple different ways we can represent that. F primed of t, well, where did that come from? From our original definition of our parametric equation, x was equal to f of t, so f primed of t, well, is the derivative of x with respect to t. That happens to be the denominator of dy by dx. It also turns out to be the denominator of d2y by dx squared. And then, well, I guess there's not really a better way to write this one. So the second derivative of these parametric equations can be calculated by taking the derivative of your first derivative with respect to t and then dividing it by dx by dt, or the f primed of t. And, well, using this second derivative again with concavity, Just like we learned in Calc 1, if the second derivative is positive, that part of the curve is going to be concave up. Second derivative is negative, that part of the curve is going to be concave down, which then again leads to where is it going to switch concavity. If the second derivative is equal to 0 or undefined, then we have a possibility of an inflection point, possibility of a change in concavity. So it refers back to what we did in Calc 1. It's just the formula finding the second derivative in parametric equations gets a little bit more involved. So, okay, now we can finish out that worksheet on the derivative, the calculus of parametric equations, section 10.3.